So this is the title of my talk, Jupiter the Bully, Saturn the Saviour, the reason for which will become clear. So it's a story of how the solar system developed and how the planets initially developed from protoplanetary dust and how the gas and ice giant planets developed. And we'll talk about all of that. And I'll introduce a couple of new theories, or they're new this century anyway, the Grand Tack and the Nice model, which help to sort of fine tune how the solar system developed in its current model as we see it, okay? So we'll start off with the cloud of gas. This is one of the clouds of gas. We heard Jason referred to the Eagle Nebula, and this is the pillars of creation right in the middle of the Eagle Nebula. Now I have my cog sheet. I might have got the lights turned down so much that I can't read it now. The Eagle Nebula is 5,700 light years away, and it's 70 by 55 light years across. And these pillars are a few light years long and about half a light year across. And this is where the stars are, This is where the stars are being formed. So what happens is a cloud of gas starts to collapse. That's perfect, yep. A cloud of gas starts to collapse. As it collapses, it starts to rotate. It sometimes splits up, but each of the bits of cloud rotate more, and they sort of, as they rotate, they sort of stretch out a bit like throwing a pizza, and we get a disk, and that's the protoplanetary disk from which the planets will develop. That is another cloud-forming gas. That's the Orion Nebula. It serves no other purpose except it's a very pretty picture, and I like pretty pictures. So this is a picture from ALMA. It is a young protostellar disk. The sun hasn't formed yet. The gas is collapsing. It's spinning around the axis that you see. And you can see the scale of it. It's about the same as our solar system. And this is sort of half pizza formation, if you like. The pizza is starting to stretch out like this, but it hasn't fully formed yet. From cloud gas to this takes about 2 million years for a sun-sized star, and to go from sort of that down to where the sun starts shining is only about 200,000 years. So it sort of spins and forms a disk, a bit like that animation. So now we have the fully formed disk. This is my year zero. So all dictators have to have a year zero, and this is my year zero. And the sun starts shining. At this stage, it is shining through gravitational collapse. All the stuff that falls into it is giving out energy from the as it falls in. So that's what's causing the sun to shine, the star to shine. But it shines pretty much as bright as any star when it's fully developed. And you can see the sun shining in the middle and the disk in a disk all around the edge. I've picked 5 other protoplanetary disks from the ALMA telescope, which we'll talk about later, just from end on to face on, just to show you how the disk forms, and that it's sort of a disk like a pizza or a frisbee so at this stage for the sun, this was 4.57 billion years ago, approximately, and most of the mass of the star has already been added, about 90%, but the mass keeps falling into the star as well as spinning around in the protoplanetary disk. And from now on in, it's the disk that we're interested, not the star, because that's where the planets form from. So what is this made of? Well, it's a representation of the interstellar gas that it formed from. So it's 99% gas, of which 98 of that 99 is hydrogen, helium, that's sort of over from the Big Bang. And there are others, such as water, methane, ammonia, and many other molecules. So there's 99% gas, and the stuff from which the Earth was formed is the dust. And that's mainly silicon and carbon compounds with oxygen, in other words, rocks. And then there's metals as well, mainly iron. So we've got iron, rock, and gas as most of what we're interested in. The silicon particles start at 0.1 micrometers, which is tiny, and it's about 1 million of those would fit in the average human cell. So they really are very small particles. And the total mass of the dust at this stage is something like 10 times the mass of Jupiter is now, or maybe a bit more. So this is what we start with, and this is what we end up with. So you can see the 4 inner planets, Mercury, Venus, Earth, and Mars, and the outer gas and ice giants. We just set it going. Hopefully it goes. A bit jerky. So you can see the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. In between Mars and Jupiter, there are the asteroids, which are mainly rocky bodies. And outside Neptune, there's the Kuiper belt, which are mainly icy bodies. I haven't included any moons. We'll just, our moon makes a cameo appearance, but otherwise no moons in this talk, unfortunately. And this is actually a scale model in that the distances from the sun to the planet are all in proportion. And if they weren't so jerky, the year length would all be in proportion as well. So that's what we end up with. The other thing I want to mention is, as well as the Kuiper belt, which is this ring, there's the Oort cloud, which is a very sparse bunch of rocks and mainly ice in a cloud about the solar system, out to about 0.8 light years, which is a significant proportion of the distance to the next star, which is 4+ light years away. So the growth of planets. So I'm going to talk now about the growth of the rocky planets and the cores of the giant planets. And these are made of the dust, which, remember, consists of bits of rock and bits of metal. So we're going to show how in four stages, how the dust turns to pebbles to planetesimals, planetesimals to protoplanet, and protoplanet to planet. And as you can see, we're going up to a centimeter, from a centimeter to a kilometer, and from a kilometer to 100 kilometers, and then on up to planet size. So we'll do these, the mechanisms are different. So we're going to start with dust to pebbles. So this is my sort of disk, a diagram of my disk, and you can see that all of the bits of dust and the gas are all rotating the same way, and that's by convention anti-clockwise as you look from the north. And these dust particles are all rotating the same way and at the same speed, so they're going to come together. And they stick together by something called a van der Waals force, which is an electrostatic force, which basically means that if you have a molecule, one end of it will probably be a bit positive, the other end will be a bit negative, and the negative end sticks to the positive end of the next molecule. So we can see that, an example of an electrostatic force. Whoops. This has stopped working. Oh, you must click something. No. Oh, great. Thank you for rescuing it. I must click one of the side mouse sort of functions. Yeah. So we can see here water, the oxygen in water. So this is oxygen, hydrogen, H2O, water. The oxygen tends to grab the electrons, leaving the hydrogen more positive and the oxygen more negative with the electrons. And then the positive hydrogen sticks to the negative oxygen on the next molecule and forms a sort of a rice pudding-like skim on the surface, which isn't very strong, but it is strong enough to hold a water strider or pond skater as they scuttle across the water. And it is strong enough so that our particles can build up to pebble size. So that's how we get from sort of dust to pebble. It is a weak force, so it can hold the water strider, but it can't hold an elephant. And no animals were harmed in the making of this talk. And so now we have a problem. We're trying to get from pebbles, which are a centimeter, to planetesimals, which we'll talk about again, which are about a kilometer. So I'm going to try and demonstrate for a moment. We have some roughly centimeter-sized rocks, and we're going to try and get them to stick together to see do they stick together. I'll give it a few moments to do this. So we have to sort of have some magic thing, and let's see whether they've stuck together. So they don't. That's gimmick number 2. And thank you. And so they will not, that may seem facetious, and it probably was, but we don't have a way in which small rocks can combine to make big rocks. But I've done it again. Oh, no, I haven't. It actually gets worse than that. There's something called the meter-size barrier. So if we remember, we have dust and the gas. Gas is under some pressure, and as a result of being under some pressure, it rotates more slowly than the dust or the solid particles. So this means that the solid particles are sort of rotating into a wind, if you like. They're being resisted in a wind. So this doesn't matter for the smallest dust particles. Help. Right, that hasn't. This doesn't matter for the smallest dust particles, which just get carried along by the gas. This isn't working.
That's just the screen. Try again. Nope, there you go.
Right. So the dust gets carried along by the gas. The big particles just blast their way through the gas and maintain their orbit. But the medium-sized particles, the so-called meter-sized particle, sort of gets resisted by the gas and sort of tails off. A bit like a cyclist slowing down into the wind. So this means that it moves inwards and it meets some more gas and it moves further inwards. I better do this because this might take ages. And it goes in and in until it crashes into the sun or breaks up before it crashes into the sun. So what we have is we've got a particle of a meter sized. We don't know how it got there, but even if we did get it, it would crash into the sun. So this is bad. There must be a solution because we're here. It gets worse again. You wouldn't expect, there's no reason to expect 2 meter-sized bodies to just form a double meter-sized body like that. Instead, they'd just crash and smash. That's what would happen. Or they'd crash and bounce. But there's no reason to suppose they'll build up. So the current research is around swirling leaves and dust bunnies. And it's a bit difficult to, that requires some explanation. I have to explain how our solar system is going to be rescued by swirling leaves and dust bunnies. Well, the gas is not just inert. It forms eddies and vortices, and it swirls around like the weather, like the wind. It swirls around. And as it swirls around, you get high pressure areas, and the particles, are meter-sized particles or centimeter-sized particles or whatever they are, get sort of caught in the middle between the pressure areas. And this has 2 effects. One is it slows down the radial drift of the bodies going into the sun. And the other is if they can gather like that, if you get enough of them, they can eventually come together through gravity. So the swirling causes the leaves, as you can see this still from a video, the swirling causes the leaves to sort of gather together, so that if this happens in space when the solar system was forming, you could imagine that it would form a clump that could come together by gravity. So the other thing is the dust bunnies. They are usually called fluffy aggregates, but at least one article I read actually referred to them as dust bunnies. So it is believed that the small bodies, the pebbles that we had at the start, don't come together like dense pebbles like this. They actually form very bodies of very low density, more like dust than pebbles. So instead of hitting and smashing or hitting and bouncing, these hit and stick a bit like this. And having gotten these bigger and bigger dust particles, we have to compress them together somehow. And that's just done by the force of the collision or the force of the wind, if you like, the force of the gas blowing against them, the force of the wind, because remember, they are moving at a different speed to the gas. And eventually then, and my animation has to move about 200 bodies here at the same time, so I have no idea how it'll perform when I click the button. Eventually, gravitational attraction will take over, not bad, and they come together and form a denser body like a rock. So that's thought to be some of the ideas of how we get around the meter-sized barrier and all these things spiraling into the sun. But radial drift is a real thing, and we'll come across it later. So we've now got to talk about planetesimals. Planetesimals are when bodies of about 1 kilometer across and up. So they can look after themselves gravitationally, they have a significant gravitational attraction, and they can attract other material to them. So we're back in business now because we've got gravity. So here's me. I've put myself onto a 2-kilometer radius, mainly iron planetesimal, and I'm about to just try and jump straight up in the air. And I spend a scary amount of time in space, but eventually I come back down again. Now here's me on a 1-kilometer radius, mainly iron planetesimal. I'm cheating here a bit because they're not mainly iron, most of them, but it's my talk, I'm allowed to. So I'm jumping up in the air, and this time I managed to jump straight off it. So whatever, up into space. So whatever support I had from my 1-kilometer body, I've lost it. So I didn't really go to a planetesimal, but I did jump up and down a good bit and do some measurements and calculations. And I reckon I could jump across off a kilometer one, but not a 2-kilometer radius body. So you get the idea. At about 1 kilometer, bodies start to have a significant gravitational force, and they can look after each other, as it were. This means that when they crash and smash, the total sum of bodies has enough, as we'll see, to bring them all back together again through gravity, like that. So this is called a rubble pile asteroid, and it's believed these are quite common among the smaller asteroids out between Mars and Jupiter. So now here is our planetesimal, a body of, let's say, 10 kilometers across. And there are lots of pebbles going past it. Some of them are crashing into it. There are a lot of smaller and larger bodies in the solar system at this stage. So here's a very schematic diagram and a number of pebbles that are about to cross our planetesimal. So if you think of the planetesimal as a spider's web and the pebbles as flies, they come across and some of them crash into it and they'll make the planetesimal bigger. But that's not actually what happens, because remember, these have a gravitational attraction, so they will arc inwards and it'll seem as if the body is much larger than it really is because of the gravitational attraction. And if we, a lot of planetary growth is about accretion. Accretion means to grow gradually by gravitational attraction of material. At least it does in this context. So we had a talk, I don't know how many people were here, by Dr. Jeff Evett, The Lost Meteorites of Antarctica. And that was in February. And this explains how meteorites can go to the South Pole. They're as likely to fall in the polar areas as they are from anywhere else. Because otherwise, it'd be very unlikely if they all travel straight, very unlikely that any of them would fall in the polar area. And this is known as gravitational focusing. So if we remember radial drift, this is where the smaller bodies were spiraling inwards because they were just getting resistance from the gas. But our larger bodies can maintain their orbit. So if we see here, the smaller bodies are all spiraling inwards, and some of them will hit the larger body as it goes past, meaning the larger body gets bigger. This is known as pebble accretion, and it's thought to play a large role in how the cores of the giant planets formed. So if we look at this diagram again, if we look now at the pebble at the top and the pebble at the bottom, the ones that are about to miss, so they both just missed the planetesimal. But in doing so, they sort of dive bomb it. So they increase in speed, as shown by the increasingly big arrows. And in order to maintain angular momentum, if the small bodies are getting bigger, the big body has to go more slowly. So this is known as dynamical friction. There's nothing much friction about it, but that's what it's called. And these small bodies then the large bodies then slow down with respect to each other. They go into more circular orbits. And when they then crash against each other through gravity, they could do so at quite a small speed, like this. So this is Arakoth. It is a trans-Neptunian object out beyond Neptune in the Kuiper belt. And it's the furthest out ever body to be visited at close range by a spaceship. So it was visited by New Horizons, which took these pictures. And I forgot what my next slide is. Yes. So I have, if you notice, I go over the other side, the two bodies of Arakoth, the smaller one is called Weo and the bigger one is called Wenu. And if you look there, it's almost like there are panels. You can see the panels. They remind me of panels on a football, but if you can't see the panels, I've drawn them in anyway. So these are believed to be smaller planetesimals that sort of all crash together. So these are the remnants of the smaller bodies that crashed to make the larger body. And it's one of the things about studying asteroids or Kuiper belt objects that they are the way they were 4.5 billion years ago. So we can learn an awful lot about the start of the solar system from them. The Earth has changed through gravity and tectonic activity and the iron falling to the center and whatever. So all of these panels are all named. You'd be glad to see I haven't put on the names, but I have put Akasa Linea is the neck, and Sky is this big crater, and there's even an article somewhere about why the impact that caused Sky didn't break Akasa Linea, the neck. So why Arakoth doesn't have a broken neck, we don't know. Right, so I said that these bodies, I hope this is the next slide, crashed at a small speed, but how small was it? And this is our next gimmick. So hopefully if you look at your phones now, I hope you should be able to vote on whether the two bodies crashed at the pace of a snail, a brisk walk, a galloping horse, a Formula One car, or Concorde. So the Arakoth is traveling around the sun at about 10,000 miles an hour. So these are all relatively slow speeds compared with that. So okay, so let's see. We've got a lot of votes. Oh, it hasn't gone on. Oh no.
Oh, there it was. I'm gonna go brisk walk, yeah.
Okay, so the 44%, nearly half of people who thought it was a brisk walk are correct. So well done to those. As you can see, my quizzes don't really matter. It's sort of a bit of fun. It's not really for, but the group collectively sort of, we can say, got it right. So well done. It was a slow speed collision, apparently. So we met Arakoth very briefly in Keith Townsend's lecture in March, if anyone was at that, Rosetta the Comet Chaser. But most of the talk was actually on, now Jason was practicing his body, Churyum of Gerasimenko, 67p. So I was practicing that yesterday as well. So this was the object of a European Space Agency visit from Rosetta. Philae is the probe that they sent down to Churyum of Gerasimenko, and it landed and sent back loads of information before, unfortunately, rolling over and getting lost, if anyone remembers from the lecture. Why am I showing this? Because this is obviously two other bodies that collided at relatively slow speeds. So, right. So we're towards the end of a stage of growth of planetesimals. This is the growth from 1 kilometer to 100 kilometers. So there are a lot of small and large bodies. The larger bodies attract the smaller bodies through gravity. And this sort of exponential thing of the larger they get, the more they get bigger, the faster they get bigger, is known as runaway growth. And runaway growth stops when most of the larger bodies, get to about 100 kilometers, and the system runs out of smaller bodies, give or take. And that is okay. So we're now going to talk about the protoplanet to planet stage. So just as a guide, it's worth introducing a few times here to sort of let people know how we're getting on in time. The planetesimal to protoplanet takes about 400,000 years. So it's very rapid in cosmological terms. That's the blink of an eye. The protoplanet to the planet, to get bigger, to get up the size of Mars or the core of Jupiter or something, or well, to the full planet really, takes 3 million years. Jupiter was the first planet to form, up to 100 million years for Earth, which is the last planet to form. So these larger bodies go under a number of names. I'm calling them protoplanets, which is the normal thing. They have been called oligarchs, which I rather like because it is the dominant bully in a sea of chaos, which seems to sum up the humankind and the solar system kind. And they're also called isolation masses, which is quite a good quite a good name, because they now become isolated from one another and they don't crash into each other as often. So here's the way I see it. This is my view of the inner solar system, circa 20 million years. So we're going from the sun, we'll say, out to about Mars level. We have maybe a few dozen bodies of a few hundred kilometers or something, of which I've drawn 14. And this is just too many bodies with too much mass in too small an area. They will gravitationally interact and pull each other about. And the first thing that can happen is that one will be thrown inwards, and that's a very unstable path. So it will then, well, let's say, crash into the sun. The next thing I see possibly happening is that one could be gravitationally slung outwards, the smaller bodies by the larger bodies. And then that's another sort of very unstable orbit, and that could interact and get thrown out further. So there it could interact with for example, Jupiter, and get flung out of the solar system altogether. We will meet a body later on that was flung out of another stellar system and came past ours recently. It's traveling so fast that it's gone 500 million miles since I started preparing this talk to now. So more often what happens is that these bodies interact by crashing, whoops, and by successive collisions, they get larger and larger until they form the 4 planets of the inner solar system, or actually 5 at this stage, but we'll come back to that. So now I'd like to look at the introduce the concept of the snow line or the ice line. In the inner solar system, the planets or the smaller bodies that we have at this stage, because we're talking about, you know, 1 million years or something at this stage after my year 0, the planets, the inner planet, the water is in the form of gas, and the planets are not big enough to attract it. They may attract other bodies, but they won't attract the gas at gas at this stage. So they should have no water. Outside the snow line, water, H2O, is in the form of ice. So therefore, the ice is solid, and it can join with the dust and the rock and the metal to form the cores of the larger planet. So they have much bigger cores. So the Earth is, well, I'm only accounting for 3/4 of the Earth, but it's oxygen silicon is rock, so it's about 45% rock, 30 or oxygen silicon and the other components of rock, about 32% iron. So basically, it has a core of iron and a mantle of rock. Jupiter, on the other hand, and the other Saturn, Uranus, and Neptune have sort of some form of core, which has the iron and rock in it in some form, and also water. The amount of water in Jupiter is a matter of debate and research at the moment, but certainly there's a lot of water in Uranus and Neptune. And this enabled them to sort of scoop up or hoover up the gas, mainly hydrogen and helium, which form most of the gas giants. And it happened in this way. The planet forms, gets bigger, which I haven't shown, and sort of accretes or hoovers out a ring. So if we were able to see a protoplanetary disk with planets just forming, we wouldn't expect the planet just to be visible, but we would expect to see the gas with rings in it, just like this. So this is the ALMA image of the disk around the young star, but then of TW Hydrae. So this could be after a couple of million years. And as you can see, there are at least 2 rings which have been effectively hoovered out, if you like, by the gas giant as it accretes more and more gas. There's another one. Okay, so we're more or less straight into a gimmick again. It's sort of an interlude. I'm going to talk about the telescope called ALMA. So why my friend ALMA? When I started out this talk, I thought there couldn't possibly be any pictures of the development of the solar system. After all, it happened 4.5 billion years ago, and they didn't have cameras then, so that we wouldn't have any pictures. This was fairly simplistic thinking. But the telescope called ALMA is more or less made for taking pictures of protoplanetary disks, and you can see it's taking loads of them. There are, 20 there. You can see it's photographed. So the first thing is, what does ALMA stand for? Does it stand for Active Laser Modified Astrophotometer, Australian Linked Multi-Detector Array, Atacama Large Millimeter Array? Or maybe it doesn't stand for anything, and ALMA is the first name of the astronomer who developed the idea. And given that there are a lot of dodgy acronyms in astronomy and space travel, I suggest it might stand for another lame acronym. I don't expect to fool too many of the people with this, but have a go if you're.
remember Alma Kogan. Anybody else?
Yeah, I did look up, there are a few Almas around. Did one of them invent this?
Imagination.
I love thinking up those names. Yeah. Okay, has everyone voted? 14. That's probably okay.
Yay.
So I'm delighted that somebody went for Alma and another lame acronym. So thank you to those who voted that way. I'm delighted at that. I'm also glad again that as an expert group, we've managed to the majority has got the right answer. So just over half said Atacama large millimeter array. So that's the correct answer. Right. That's a picture of Alma. So it has 66 radio telescopes all working together as an interferometer. And you may remember that in the challenges of the SKA project in May, for anyone who's here, Dr. Anna Bonaldi showed pictures of the telescopes that are spiraling outwards. And you can see these same spirals here. And I have two explanations for these. One is if as the spirals, it's the right way for when the Earth rotates. And also it's much cheaper to wire them up that way. What happens is that the telescopes that are way out at the side give the magnification, if you like, and the telescopes in the middle get the light in. So they give the sort of the color to the picture, if you like, and the ones out at the side give the magnification. So that's why you put more in the middle to get more sort of light in, or radio light. They are 5,000 meters high on a plain in the Atacama Desert. And that's, I call that high and dry. They work at the very far end of infrared, on the borderline between infrared and radio wave. So it's millimeter and submillimeter. So while normal radio astronomy works in the 1 millimeter to 10 millimeters, this is 0.32 millimeters to 3.6. This is right at the edge of the rays that get through the Earth's atmosphere. In fact, they don't really. They are absorbed by water, and that's why they put them up high so that most of the water vapor is below them, and dry in a desert. So that makes sense. The long wavelength compared with infrared allows the observation of cold gases, and hence ALMA can see the whole of the protoplanetary disk. What happens roughly is that if you take a very hot star, it shines in the infrared, the ultraviolet mainly, but also in light and infrared and millimeter rays. If you take a star like the sun, it doesn't shine much in the ultraviolet, but it shines in light and infrared and millimeter rays. Planets, or our bodies, or the wall there, emit infrared, but no light, well, unless it's reflected off it, but also millimeter. But when you get right out into the coldest reaches of a stellar system or of a protoplanetary disk, it really only radiates in the millimeter. So by observing in the millimeter, we see the whole protoplanetary disk from the sun right up to the sort of Stygian depths or the Plutonian depths or whatever. That's why sort of ALMA was made, really. A couple of other things it's done. It discovered phosphine on Venus, or at least it discovered it, they published it, and it was sort of immediately countered and refuted. They didn't really have enough evidence. The thing about phosphine is it's believed only to be made by life. It can only occur if made by life. So if you found phosphine on Venus, that would be very interesting indeed. But it does you can get a spectroscopic picture, and you can look for elements, look for molecules rather. So this is This is 2I Borisov, a comet. This is the body that came from from another stellar system. It came past the sun, quite close to the Earth, or not very close, but past the sun, fairly close to the Earth, and went out again. And as I say, it's moved 500 million miles, or maybe it was 500 million kilometers since I started preparing this talk to now, and it's now some way out past Neptune. But the point was they managed to observe HCN, hydrogen cyanide, and that's fine. But they also observed a lot of carbon monoxide, and that would not be present, apparently, in a comet from our stellar system, the solar system. So that gave evidence that it was from another stellar system, and the fact that it was whizzing past it, whatever, 500 million miles every few months. So that's an alien comet. So back to our formation of the stellar system. There are 6 problems which I have found with the model so far. I'll sort of read these first and then explain them. Why is Mars so small? Why do we have water on Earth? What caused the late heavy bombardment? How do we explain the position of Uranus and Neptune? How did the Kuiper belt form as it is now? How do we explain hot Jupiter exoplanets? Now that may seem like Greek to you at the moment, but we'll explain it. This is my diagram to explain how Mars, why Mars should be bigger. The yellow dotted line is, so I've drawn an inner solar system with 3 protoplanets, Mercury, Earth, and Mars, or their protoplanets. Don't ask me about Venus. It took me ages to set this slide up. So I only managed to do it for 3 protoplanets. The yellow dotted line is the orbit, and the white line is the area of gravitational influence. So there are, I've counted them, 16 dots that are in the protoplanet, or the gravitational influence of Mercury, 53 for Earth in this diagram. Obviously, it's a highly schematic diagram, and 100 for Mars. So Mars should be at least as big as the Earth, if not bigger, but it's actually only 1/9 the size of the Earth by mass. So why is it so small? That's question number 1. The next one is, why do we have water on Earth? If we look at the right of the diagram first, and you remember from the snow line, inside the snow line, water was in the form of gas. So it should not have accreted to the small bodies that were there then. There's no way that it could have done so as a gas. When it got to the snow line, then the major planets, the larger planets, Jupiter, etc., could accrete it, but there shouldn't be any on Earth. If we look at the diagram on the left, that's the amount of water on Earth. It doesn't look a lot, but it is covers a good bit of the United States. Obviously, it's an American picture. They cover the United States. And so there's quite a bit. So if the Earth's water were put in just a sphere and was circling another planet as a moon, it would be the 8th biggest moon, just about, and it would be the 19th biggest body in the solar system, with obviously Sun as number 1 and Jupiter as number 2. They go down quite quickly. So there's quite a bit of water on Earth, and we don't know how it got there. That's question 2. So if we ask what caused the late heavy bombardment, I suppose the first thing to say is, what was the late heavy bombardment? When they went to the moon, they found the rocks on the moon. They expected them to be sort of 4.5 billion years, the same as the solar system. But they found a lot of them were sort of 3.9 billion years, 600 million years younger. So they concluded that there was a bombardment, which I've been describing, when the moon was formed. And then there was a quiet period, and then there was a later bombardment at 3.9 billion years, 600 million years later, sorry. Running away with my notes. And that's the late heavy bombardment. The sort of clue is in the name. That's our problem number 3. The next is the position of Neptune and Uranus. 30 astronomical units is the distance. So what's an astronomical unit, I have to say first. An astronomical unit is the distance from the Earth to the Sun. That's given as 1. and it's a useful measuring tool for the solar system. So 30 astronomical units is where Neptune is now, but the disk is believed to have been far too thin at that point for a planet the size of Neptune to have formed. Same for Uranus. That's problem number, what am I up to now? 4. The Kuiper belt before 600 million years was believed to have been 10 Earth masses. That circle with a cross and it represents the Earth. So it's believed to have been really very thick, 10 Earth masses, but now it's only about 0.1 Earth mass. So what happened to the other the 99% that's not there now? And finally, how do we explain hot Jupiter exoplanets? When they first discovered exoplanets, planets going around other suns, they were really quite shocked to find that some of the first ones they found were Jupiter-sized planets, or bigger, orbiting around stars like the sun, with orbital periods of like 5 days or 4 days or a week or something. Very close in, very big, very close in. And there's no way, according to the theory that I have described, that a planet of that size could form so far into the sun. So what are they doing there? So those are my sort of 6 questions that we will answer by the end of the talk. So I would like to introduce the concept of the grand tack. And this is one of the new ideas, one of the 2 new ideas I'm sort of bringing in. The grand tack was written up about 2011 and happened at about 5 million years. I'm getting really stuck with my notes. 5 million years after my year 0. So what happened is that the gas on the outside of Jupiter is moving more slowly than Jupiter and is trying to slow it down. The gas on the inside of Jupiter is moving faster than Jupiter and is trying to speed it up. There is more gas on the outside, so the gas on the outside wins, so Jupiter slows down. And as it slows down, it moves inwards. That's a bit counterintuitive. You'd expect it to attract, but it's all about rotational movement and not direct attraction. So as it moves in, it disrupts the gas disk. It sort of starts to hoover it up and disrupt the small bodies. And as it gets in there, there's still more gas on the outside than there is on the inside. So it's going to slow down further. So it's going to, like our meter-sized bodies early on, it's going to spiral completely into the sun and crash into the sun. Now, we did have the comet that crashed into Jupiter some time ago that caused quite a big bang. Well, this would be a really big bang. But obviously it didn't happen. So if it went all the way in there, into the sun, it would have disrupted the bodies that were at that stage forming the Earth. And the Earth wouldn't have formed, or it would have been very much smaller, and we wouldn't be here. So if we look at this in one dimension, it would have disrupted the sort of protoplanets and planetesimals, shoving them outwards as it went into the sun, leaving not much to form the Earth. But what actually happened is that Jupiter came in to the level of the orbit of Mars and then stopped. So why did it stop? There's nothing in what I've said that it should have stopped. So it stopped there. So it didn't disrupt all the stuff that eventually formed the Earth. And what actually happened was, so this is the sort of, sorry, I'm just going back, the Jupiter the bully bit. Jupiter bullied all the, well, should have bullied all the stuff that would have made the Earth. So that's Jupiter the bully. And then we have Saturn. The same thing happened to Saturn. Saturn formed a little bit after Jupiter, and it also had a similar gas-driven migration, and it came in and positioned itself a bit out from somewhere in the asteroid belt. And they came into a 2 to 3 resonance. There are 3 Jupiter orbits there for every 2 of Saturn. It's a bit jerky, but there are. And we have to take the mathematicians' word for this, and even astronomers, physicists didn't work this out, it was mathematicians, that when that happened, the Jupiter and Saturn moved outwards, as in Saturn sort of dragged Jupiter outwards into roughly the same position as they are now and saved the Earth, the forming Earth. So we have Jupiter the bully and Saturn the savior. In fact, this outward spiraling would have happened until, as long as there was gas there, it would have gone out, they would have gone out further. But the next thing happened is the gas disappeared. So it was blown away by the sun became hotter, it started radiating in the ultraviolet, and the ultraviolet basically blew the gas away. And once it happened quite quickly. And the sun went from the proto-sun bit to what's called a T Tauri phase. And I'm not going to explain that for two reasons. Firstly, I don't really know. And secondly, it's not really the subject we're talking about. So this is the Earth at, we'll say 10 million years, sorry, the solar system at 10 million years. We have the 4 planets, the 4 gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. And we have smaller bodies, the Earth and Mars and etc. haven't yet formed. So this is the asteroids and all the stuff that's going to form the inner planets. And we obviously have the Kuiper belt, and there are always a few stragglers in the middle. So that's the solar system. In the next 100, from 10 to 100, or the next 90 million years, 2 things happen. There's rocky planet formation and nuclear fusion starts in the sun. At 100 million years, well, it doesn't take a clairvoyant to work out that something bad is about to happen here. And this is Theia, the protoplanet Theia, hitting proto-Earth. And that happened at about 100 million years. And it works. And the sound works even. This is a NASA diagram of how it might have happened. And that bit is the moon. Yeah. That's. And I saw something somewhere recently that described why that there may be observable chunks of Theia still sort of in Earth. Hey, that's just the same thing happen more slowly. We've seen it as it is. So this is the solar system at 100 million years. So we know it's fairly much like it is at the moment. Our Kuiper belt is too thick. There are a couple of other things, but we have the 4 inner planets, which have drawn their orbits and not the planet. We have the asteroid belt, and we have the 4 giant planets. So I'd now like to introduce the other trick up my sleeve, as it were, the Nice model. Nice model because it was invented in the University of Nice in the south of France. And this relies on the fact, this gets a bit complicated, so you have to bear with me. Now, Jupiter is 5.2 astronomical units from the sun. And if you remember, an astronomical unit is the distance between the Earth and the sun. So Jupiter is 5.2. Its year length now is 11.6 Earth years. Saturn is 9.22 astronomical units, and its year length is 29.5 years. So the ratio of Saturn's year to Jupiter's year, just dividing that by that, and you get 2.5. So Saturn's year is 2.5 times longer. 100 million years ago, it was believed that Jupiter was further out from the sun at 5.6 astronomical units. Its year was longer at just over 13. Saturn was closer in at 8.6, and its year was shorter. So if you divide Saturn's year by Jupiter's year then, you get 1.9. And if it was 1.9 then, and it went to 2.5 now, at some stage it had to cross exactly 2. So, yeah. And this is how it happened. So the Kuiper belt objects came under the influence of Neptune's gravity and were gravitationally slung, as we've seen a few times in this lecture. They get gravitationally slung inwards. And they then come in under the influence of Uranus's orbits and then Saturn's orbits. They both tend to sling them inwards. But because Jupiter is so much bigger, it tends to sling them outwards, all the way out of the solar system altogether. So Neptune bowls them in and Jupiter bats them out again. And what happens is, again, we have to conserve our angular momentum. And as the large planets fling them in, this is Saturn, Uranus, and Neptune, they move out a little bit. Not very, very little, but when they do this a few 100,000 times, they move outwards a bit. And Jupiter, in flinging them all the way out, moves in a little bit. So Jupiter is moving into a shorter year, Saturn is moving out to a longer year, and the ratio increases until it increases from 1.9 to 2. And at that stage, the fact that Jupiter and Saturn are every few years, they're alternately pulling on the system and pushing it. This creates absolute gravitational chaos in the whole of the outer solar system. And rather than describing this, I've got a video which I hope works. Please work. Oh. Huh? Be patient. It's a dreaded ring. So what's happening here is we have this very thick Kuiper belt. Jupiter and Saturn are about to come into this 2-to-1 resonance. And you will see when it happens that these are 4 million year snapshots. Between 4 million years and the next, there's absolute chaos for the Kuiper belt objects. You will also see that Uranus and Neptune move outwards because of this. This is a computer-based model. You know, they put the rules in, put all the bodies in, and just press go, and boom, yeah. And Uranus and Neptune actually change places in this diagram. So at the start, which we'll see in a moment, you can see the blue one is on the outside here, Neptune. I think it goes back to the start next. Oh, I don't want to watch again. Do you want to watch it again? Or? No, I don't. Okay. Because it goes onto YouTube then, and I lose my lecture. Can I get off it? But yeah, the bottom left down here, that's it. Yep. So what we've had from beginning to end is that Uranus and Neptune have gone further out. They've changed places. The blue one is Neptune, the bright blue is Neptune, and most of the Kuiper belt has been dissipated. So where has it gone? Well, all these bodies have been slung outwards to form or part of the Oort cloud, and the Oort cloud is a cloud of bodies surrounding the solar system, going out to about 0.8 light years. It's never been found. It's believed to be there, and it's believed to be the source of the long period comets that we see. So some of them were flung out into the Oort cloud or out of the solar system altogether. And what happened to the rest? Well, some of them were flung inwards, and that caused the late heavy bombardment. So that's once we've accounted for that, we have the solar system pretty much as it is now. But just we've answered the question. So the problems we had, why is Mars so small? Well, in the grand attack, Jupiter disturbed or accreted the mass that would have formed a larger Mars. If you remember, it came in and out again. That's the tack. It's like a yacht coming in and going out again. That's tacking. What caused the late heavy bombardment? Well, we've just done that. It was caused by the disruption of during the disruption of small bodies, mainly in the Kuiper belt at the time of the Nice model disruption. Why do we have water on Earth? Well, the Earth was bombarded with water containing asteroids, probably more from the asteroid belt than from the Kuiper belt, but from one or the other. The water came into the Earth afterwards and wasn't there at the start. Whoops. Position of Uranus and Neptune, well, they couldn't have formed as far out as they did, if you remember me saying that, but they didn't. They formed further in and moved out. And how did the Kuiper belt form in the way it currently is? Well, they were just the larger Kuiper belt was disrupted at the time of the Nice model. And how do we explain hot Jupiter exoplanets? Well, they were formed further out from their protostars and moved in by some form of gas-driven migration that I described. And one of the questions I didn't ask, but I'm about to answer, the distribution and position of the asteroids is quite well explained by, physicists think it's quite well explained by the Grand Tack. So we've explained quite a few of the things in the how the solar system is as it is now. So just at the end, it's time to look, is this really right? I mean, I've spun a good yarn, I hope. And is it just that, or did it really happen this way? Well, I think the basic model of the planets, the disk spinning around and fluffing out, so the thing is fair, and the planets growing from the bottom up is very likely in the case of most planets. The finer detail, there's a lot of current research going on to try and iron out the sort of finer problems. Planets, we know as of this century that planets migrate, so they go from in to out, and they can also go out to in to out and out to in, whichever, as I've described. The Grand Tack is probably still a popular theory. I like it, but there are other theories that explain, for example, why Mars is so small, but it's a good theory, isn't it? The Nice model is becoming better established. It's thought that probably something like that did happen, despite the fact that the late heavy bombardment depends on the Nice model. Well, the late heavy bombardment is recently challenged, and people are not so certain that there really was a late heavy bombardment. But they are all sort of fairly current and reasonable theories. One thing to say is that most exoplanetary systems are very different from ours. So the idea of explaining the rocky planets inside and the gas planets outside really fits together rather nicely. But that's not the way exoplanetary systems are. There are a lot of Neptune-sized planets or nearly Neptune-sized planets right in where the Earth is. So we're not quite sure whether this model is complete or whether there's more to learn. I'm sure there's more to learn. So hopefully I've had a great fun preparing this talk. I've spent a lot of time in it, and I've really had great fun learning about it and preparing it. And I hope I've been able to pass over some of that enthusiasm and information, and that I hope that everyone's enjoyed it. I'll just leave a sort of a chronology of what I've talked about, but I'm not going to go through that. I'll just leave that on the screen. But that's it. Thank you very much for coming, and thank you for listening.